just doing a quick thing on 6.1, and then we'll get into 6.2. So, are people writing this? That's fine. Alright, so this might be a little bit more difficult if you haven't taken physics. I'll try to go slow and clarify all the stuff there that I'm interested in. This is a meters per second graph, so you're driving down the street and for some reason we're meters per second instead of miles per hour. You go for 5 seconds, let's say. So this is 5. How far did you travel? 100 meters. So the units is meters. And I want to show you why that happens. So, how'd you get 100? It's multiplied, right? So you're multiplying 20 meters per second times 5 seconds. So what happens to the seconds is they go away, and you're left with 100 meters. Finding this area here is integrating. That's what integrating does. So when you find the area of the curve, or line, whatever, you're going, I call it like up a level. So I think about it like, let's put it in terms of position, velocity, and acceleration. So this might be in meters, this would be meters per second, and this would be meters per second squared. Well, if I'm taking the derivative, I go down the list. If I'm integrating, which is what all of second semester is, we're going backwards. We're going up the list. So this is supposed to be an example of like if I integrate meters per second, I get meters. So if I integrate meters per second, if I'm at the area under that curve, I get meters. So if you remember when we did derivatives, we divide by s squared. If I kept going, it'd be divide by s to the third. Like you add an s on the bottom every time. You're integrating. It's the opposite. You're like getting rid of an s on the bottom because you're essentially multiplying by seconds when you go up that list. Other thing I want to make sure of is that you understand when they say the area below the curve, they mean the area between the curve and the x-axis. So I would say this as like the area below the curve. Like that's how it's phrased. What it means is by below is like closer to the x-axis. So that would be a negative answer because it's below. That's really the two things that I was worried about. And we'll hit those like as we go forward too. But questions on 6.1, anything real quick there? Alright, let's look at 6.2. So if you remember in derivatives, you guys learned the quotient. What's that called? Remember the derivatives thing where you have to do a limit of f of x plus h minus f of x, and you have to expand everything. This giant long process, difference quotient, to find the derivative, and then I was like, oh, the derivative of x squared is 2x. So kind of the same thing happens, except the AP test is more concerned about the long way that we learned first. So we are learning a long way to do this. It's kind of tedious, it's not that bad, but then after we do that for a couple of days, I'll show you the shortcut trick. So just so you don't get pissed at me when I show you a faster way. So what we're going to do first is estimate the area under the curve with rectangles. So this website is a pretty good demonstration of it. So I want to talk about a couple things on here, what they mean, and then change some things and just kind of show you how it works. So this is how it's written. What this is asking for, or what this is demonstrating, is the area under the curve. I can't write it this way. So the question here is, find the area under the curve between -3 and 3. So this is y equals x squared. We're estimating the area under the curve between -3 and 3. And so what we do is estimate using rectangles. So I'm going to explain it with the left-hand method first, but there's also right, middle, and trapezoid. The left-hand method says that I look at each interval. So I'm looking at like this. Can you guys see when I wiggle the mouse around? Like where the mouse is? Okay. So I want to estimate like the area under this curve. One way to do it is say let's make a rectangle. Because I know how to find the area of a rectangle. It's just based on its height. So the base is going to be like this distance down here, which is, let's just say it's 1. It's not, but I don't know, 0.9. The height of that rectangle is the question. Are we going to use the left-hand endpoint and call that the height? That's the left-hand method. Are we going to use the right-hand endpoint and call that the height? That's the right-hand method. Or are we going to use the middle and call that the height? So those are 3, and then there's a 4th one, but that's just the average of 2 others. Let me show you a different curve and just kind of show you a similar idea. So this would be like a terrible estimation. But you can see like the left, right, and middle thing a little better here. Left-hand estimation method would be, okay, for this rectangle down here, use the left-hand endpoint, determine the height there, and pretend it's the height the whole time. Use the left-hand endpoint, like between 1 and 2 here. I wish it would come out even, but can't really. Use the left-hand height for this interval, and then pretend that's the height the whole time. Find the area of that rectangle. So is this method overestimating or underestimating the true area? Underestimating, because you got like these white spaces under, right? Why is it underestimating the true area? What is true about the function itself that makes it so the left-hand endpoint will always be smaller than the right-hand endpoint? Close. Because it could be concave up like this, and it wouldn't be true. It's increasing. Because if you are increasing, I look at the left-hand endpoint, isn't that going to be a smaller number than the right-hand endpoint? So you're going to be underneath the curve. If you're decreasing, it'd be the opposite. So there's my left. Middle. Let's look at this rectangle on the right. So the interval is between like 2.5 and say 3.2. So the base is, let's say, 0.7. The question is, what's the height? The height, we're at the middle, means we take the midpoint of these two endpoints of the rectangle, find the height there, and pretend that's the height the entire time. And there's no automatic rule where this is like an overestimate or underestimate. It just depends on the function. Right, so if you think about this rectangle on the right-hand side again, we pretend the height on the right-hand side is the height of the entire rectangle, of that entire thing. And so here we're overestimating, right? Because the right-hand endpoint is bigger because the function is increasing. And then there's trapezoid, which, so that would be like 1, that's a trapezoid, I guess. They're saying you take the left-hand point, the right-hand point, connect them, and it makes a trapezoid, and then we add up the area of those trapezoids. That is going to be an overestimate in this situation. Why? Why is that line between the two endpoints always going to go over the top of the curve? It's concave up. Now is when you want to say concave up. If we were concave down, those lines would go underneath. Okay, and then the other thing I want to show is like, I think fairly obviously, but if I make more rectangles and find the area of these rectangles, what happens to my errors? They get way smaller. And what happens to my accuracy? You know, that's like one trapezoid. That's terrible. But if I make more and more and more rectangles, it becomes accurate, and that's what an integral is. It's the adding up of these rectangles where the limit of the base of the rectangle is 0. So like the base is so skinny that it's not 0, but it might as well be 0. And then you're adding up all of these little tiny rectangles to get the area underneath the curve, which is between the curve and the axis. So that's like a general overview. Any questions I can answer based on that? Okay, then let's start looking at 6.2 in your book. Remember when I was like, are there any other questions on 6.1? That would have been a good time. Okay, that is what, like, I just went through that in like way more detail, so don't worry about that part. I want to do the problems, but I'm zoomed in. Hold on. Okay. Left Riemann sum on the interval 2 to 8. Use 3 subintervals. I'm looking for 2 to 8. I want to know that area. The length of the interval they're asking me for is 6. They're asking me to divide it into 3 subintervals. So each subinterval is going to be 2 units long. So I'm going to have an interval between 2 and 4, an interval between 4 and 6, an interval between 6 and 8. And I'm just adding up the areas of these rectangles. The question is, what do I use for the height? So left-hand interval, I look at each, or left-hand sum, I look at each interval, I go to the left-hand endpoint, and go up, and I pretend that is the height for that entire interval. So it's obviously an underestimate, because the function's increasing, so when I start here and leave it there, I'm going underneath where it actually is. So what's the area of that rectangle? Well, what's the base of the rectangle? 2. Every rectangle is just base times height, right? The base of that rectangle is 2. What's the height of the rectangle? Okay, so I'll accept 6. Give me a more general. What's the height of the rectangle? What will always give me the height at 2? F of 2, yeah, so they're the same, right? So if I find f of 2, isn't that going to be that y value? It just means like plug 2 into the function. So like if I plug 2 in here, this would be 8 minus 2, and I get 6, so that's the height, that tracks. So f of 2 means you're going to do like 2 times, in this case f of 2 is 6, and sometimes you can tell that from the graph, and sometimes you have to actually plug in to find out what that's going to be. So that's my first left-hand rectangle. I got 2 more. So then I'm going to add the area of this next rectangle. Well, the base of that rectangle, also 2. And for the height, am I going to use the 4 or the 6? For my x value that I'm going to plug in, am I worried about the 4 or the 6? For this left-hand side, I'm worried about the 4. So I pretend that's the height the entire time. It's an overestimate now because the function is decreasing. And this will be 2 times f of 4. And in this case, I can tell f of 4 is 8. But if I couldn't tell by looking, or if I didn't have a graph, you just plug into the equation. Then 1 more. So then I got this green one. I'm going to go to the left-hand side of that end of the interval. Up and pretend that's the height the whole time. And the area of that rectangle is 2 times f of 6. So you use the left-hand parts of each rectangle. You will never plug in f of 8 in a left-handed sum because f of, well, in this one, you couldn't plug in that number because that's never going to be on the left-hand side of it. And then you would figure out that what that is. So this is, I don't really care that much about the answer, but I feel like I should put it 12 plus 12 plus 16, so 40. But the process is more what I'm looking for. Question on the left-hand method at all? For the right hand, can I erase this? Yes? Yeah, you're still right. So the right-hand sum is extremely similar. You have 3 subintervals to cover 6 units, so each rectangle is going to be 2 units wide. But now, so the base of this rectangle is 2. But now the height of it, I'm going to look at the right-hand side of that interval between 2 and 4. Pretend that's the height for that entire interval. So this will be 2 times f of what? F of 4. And then I'm going to have 2 times f of 6. I don't know if you guys are not working or if Strip's the only one that knows it or what. And then plus 2 times f of. Give me thumbs up, down, sideways. Okay. Why is that my answer like this? Okay. So then you would plug this in, like if you have the graph, great, you can read it. If not, you might have a table. You might have an equation that you have to plug into, but that's the general. Is that okay for right hand? Can I erase that? And then midpoint. Again, I have 6 units to cover with 3 subintervals, so every subinterval is going to be 2. But now I'm looking at the midpoint. So I'm pretending that's the height the whole time. So the base of that rectangle is still 2. What's the height of that rectangle? This is where I need people to answer. I don't think you know what's going on. What's the midpoint of 2 and 4? It's 3. So the height of that rectangle, we're going to use the 3. And we would read it off the graph. We would plug into the equation. We would look at the table, whatever we have. Plus 2 times f of 5. My next one's 4 to 6, so I go to 5 and pretend that's the height the whole time. And then the last one is 2 times f of 7, right? Trust that your thumbs up means you're good. And then trapezoid, I don't ever do trapezoid. Trapezoid is the average of LRAM and RRAM. What are LRAM and RRAM? Left and right. So this is actually like left-hand rectangular approximation method. Right rectangular approximation method. If you average those two together, you can kind of see it. Like if I look at this rectangle here, the LRAM would be here, the RRAM would be here, and the trapezoid makes it there. So it just kind of cuts that part in half, and it ends up just being the average of these two. So typically, it's easiest for me at least to just find left and right and then average them together. If you really wanted to get fancy with the equation, like I would probably never do this, but it would be your base is 2, and then the height is going to be f of 2 plus f of 4 divided by 2, because you've got to average the left-hand endpoint and the right-hand endpoint. Plus, and you keep going. I wouldn't do it this way, but just for the sake of showing different methods. Then it'd be like between 4 and 6, and then it'd be between 6 and 8. Questions on left, right, mid, trapezoid? Okay. You guys don't. So I would just do left and right. You're not going to have to know this method. Okay. All right. We already kind of talked about this next stuff, but let's just make sure that we all understand. So left Riemann, if it's an increasing function, the left-hand endpoint is going to be lower than the right-hand endpoint because that's what increasing means. It gets bigger. So if we're lower over here, are we overestimating or underestimating? Underestimating. The right hand would be the opposite. So that's over. Decreasing function, the left is going to be bigger because the y value on the left will be bigger than the y value on the right. So that's over. And then decreasing the right hand side will be, that'll just be 0. Those okay? Okay, erase. Then what do they do? Their concavity next. So the concavity only you can only really use it if you do a trapezoid rule. So concave up. If I do a trapezoid here, recalibrate that. If I could draw a trapezoid correctly here, it goes over the top. Hopefully you can kind of tell that. It's going like that, and I have a point here and a point here, and I draw the trapezoid. It's going to go on top of that part. And then here, go underneath it, right? So you have like here, that go like under it. So that would be under. All right, from a table. So it's the same idea. It's actually, I think, easier from a table. Right, left, mid. So, right hand endpoint, 4 subintervals. 4 subintervals is good. I've got 4 subintervals, like between 0 and 3, between 3 and 6, 6 and 9, 9 and 12. So look at your first subinterval between 0 and 3. We're just doing base times height, plus base times height, plus base times height. Add up the area of rectangles. What's the base of this first rectangle? First rectangle. It's 3. That makes sense, right? Okay. And then the height of that, well, we're going to look at the right-hand endpoint, which is 3. And what's the height at 3? Is 13. So that's really like 3 times f of 3. It's just I know f of 3 is 13, so I can write it down. So there's one number in that chart that I just don't care about. It could be anything, and it wouldn't change my answer. What number is that? What's that? The 7. These all matter because I need to know how far apart they are from my base. This just can't be, I just meant for this question. But for the right hand one only, that can never be the right hand side of anything. So that just will not matter. So this would be 3 times 13 plus 3 times 18, because that's on the right hand side of this interval, plus 3 times 3 plus 3 times 27. Left hand, what number on that table becomes completely irrelevant if I'm doing the left hand side? 27, because that can't be on the left hand side of anything. My bases are all still 3, so this first subinterval, those are 3 apart, and the height is based on the left hand number. So 7. 3 apart, so that's my base. Left hand number is 13. I got tired of doing parentheses. Questions there? What's up? You can. I'm not doing it every time, like as the as like the rule, because sometimes these will be different. It'll be like 0, 2, 6, 12. Like the gaps are different. So I don't want to get you in that habit and then have to like break it. But like when you're calculating, yeah, there's no reason you can't just do that. Once you know that the bases are all 3. Okay, midpoint. Notice there's like 2 subintervals. Reason for that? If I made 4 subintervals, if I just look at my first one, my base is 3, and my height would be f of 1.5. It would be like the y value based on the middle of these, and you don't have f of 1.5, so they can't present it that way. They're telling you 2 subintervals, so now you're going 0 to 6, and 6 to 12. So my first interval has a base of 6, and then the height is what? 13. So 0 and 6 are the endpoints of that interval. I find the midpoint and find the y value of the function there. So that's going to be 6 is the base and 13 is the height. Plus, and then in my next one, 6 is still the base. To find the height, your endpoints are 6 and 12, so what's right in the middle is 9, and you use that to find the height. That's there. Is that alright? And then the trap, I already found left and right, so I was averaging. I'm not going to do like that big one. I think that's it. Is that all? Is that all it does? Okay, go ahead and get started on 6-2. How's you gonna do 6-1? Number 7?
I mean, you pretty much just did how it's anyways, so that's fine.
Really? Just curious what it is. Oh, gotcha. Yeah, so it's like the areas.